Welcome to the talk. My name is Yongli. I'm a PhD student in George Mason University. We create a document processor called rtDown for executable linear algebra papers. This is a joint work with Dr. Shoaib Kamil from Adobe Research, Professor Eric Jacobson from University of Toronto and Adobe Research, and my advisor, Professor Yotam Gingold from George Mason University. rtDown is an environment for reading and writing scientific documents. Instead of writing formulas in LaTeX, you write them in rtLA. By compiling the math, rtDown augments the paper with clickable definitions and warns you when you have forgotten to describe a variable. The compiled math can be used to generate figures. Updating the formula will change both the math output and the figure. Researching and disseminating scientific ideas relies on written communication. There are many literate programming environments, including Notebook, Router, and Observable. Some of these support prose-determined order. These duplicate math and code. Many approaches to reactive documents such as ID, Tangle, and SIGGRAPH have been proposed. Some papers focus on authoring and publishing scientific articles, such as Distill, Elsevier, and Nota. In contrast, rtDown is focused on helping users correctly author, read, and experiment with mathematical formulas in scientific documents. Languages for compilable math include Fortran, Lean, Julia, and rtLA. We can build rtDown on top of different languages here. We chose rtLA since it resembles the equations in paper and can generate code for different backends. Various math augmentations, such as SIGGRAPH and Penrose, have been proposed to facilitate understanding mathematical notation in papers. We use some of these augmentations in our viewer. We did a formative study for rtDown. Before that, we have two design goals. The first is to support authoring, reading, and making use of correct and reproducible documents with minimal authoring overhead. The second is to provide ecological compatibility, which means we don't want to change or restrict what authors put in papers, such as prose, math, figures, and tables. And we want minimal changes to how they write. For example, we prefer plain text documents. To inform our design, we thoroughly analyzed 156 papers from the SIGGRAPH North America 2020 technical papers, collecting both quantitative and qualitative observations. We found that they all appear to be written using LaTeX. Other observations include prose organizes the document. Mathematical expressions appear between paragraphs of prose or inline. Math symbols are often used before they are defined, as determined by the prose. Let's see a typical example from this paper. If we zoom in the 6th and 7th pages, we can see that equation 1 defines a function c that uses w, which is defined in the second equation. Meanwhile, omega in the second equation is defined in the fourth equation. For each equation, there is a prose block after the equation, describing all the symbols in that equation. We also found that symbols may be reused, but the different context is clear to the reader. For example, the M symbols have different meanings in these equations. A symbol may appear in both derivations and executable formulas. For example, the equation 12 is a derivation for the function u, while equation 14 is actually implementable. Symbols and functions may be defined via conditional assignment, which is a simple form of control flow. Functions make use of a variety of implied semantics for parameters and pre-computed symbols. Quantitatively, we manually observed the 916 function definitions across the 156 SIGGRAPH papers. We take an empirical approach to categorize these equations. Here is the overview of them. 96% use parentheses for parameters. 91% rely on implicit parameters. 17% interpret the function's subscript as parameters. 15% have seemingly unused parameters. 6% are defined via conditional assignment. 4% use square brackets for parameters. 2% interpret the function's superscript as parameters. 2% interpret the parameter superscripts as additional parameters. Based on these findings, we extend the grammar and implementation of rtDown to include the support for local functions. In addition, pseudocode sometimes present while compilable code isn't. There is no literate programs. We design rtDown based on the previous formative study. Just as in LaTeX or many other Markdown formats, the prose is written as plain text with occasional markup commands. Authors must declare context for their symbols. This allows better symbol and formula reuse. Later context declarations override earlier declarations. The context disambiguates symbol reuse and corresponds to a concept of reusable modules. One appearance of a symbol in the prose deserves special attention: the text describing the symbol. Detecting the span of this prose cannot be accurately automated, so we require authors to annotate such spans. Authors can write executable mathematical expressions in different rtDown blocks and inline rtDown formula. rtDown requires the type declarations for all symbols not appearing on the left-hand side. Original rtDown can handle multiple equations in papers. We need to add new language features. We add local function support based on the formative study. In order to handle math appearing out of order, we add symbol diffuse analysis. We add modules from another rtDown file to support a different context. We also modify mathsjx output to include the metadata. rtDown executes Python code blocks, which allows authors to generate figures programmatically. The Python code can access the compiler functionality of the document as a module. Authors can also edit rtDown formulas and Python code for figures directly in the viewer side of the authoring environment. rtDown helps authors write correct math and complete prose. Error messages appear whenever the user's formulas contain incompatible indices, dimensions, types, or erroneous syntax. The editor displays the rtDown compiler error message and highlights the appropriate line in the source. When symbols are not described with prose, they appear with red underlines in the viewer. rtDown's paper reading environment provides several useful interactions that use the metadata. We were inspired by Scholarify, but aims to support all enhanced reader environments as a paper writing environment. rtDown displays the glossary on the right side of the window in a fixed position as the page scrolls. The glossary in rtDown is context-dependent. When the page scrolls to a different context, the glossary updates automatically with the relevant symbol list. This figure shows the visualization we provide when clicking on the symbol in an equation. When clicking an equation, rtDown highlights the terms involved in symbol's definition, as well as downstream uses of the symbol. rtDown solves a graph coloring problem using a greedy technique to ensure symbols in the same equation have different colors. Here is the clustering example. We generate the output by compiling the source code. The initial source code uses L1 norm to calculate the distance. We can change the math to use L2 norm, which is a more common norm. rtDown will update both the math output and the figure that relies on the generated code library. The new cluster centers have changed and are now heavily influenced by the outliers. We can also click the figure to update the figure code. In this case, rtDown will only rerun the figure code. The generated code libraries are saved into files and it can be used outside of the hard-down reading and authoring environment. We'll show examples of that in our case studies. For the implementation of hard-down, this figure shows the overall structure. The web-based authoring GUI displays the editable input source and output paper reading environment side by side, leveraging an embeddable code editor. The GUI communicates via POST request with the server running the Python-based Tornado web framework and asynchronous networking library to run the hard-down document processing. To speed compilation, hard-down catches rtDown code and only recompiles it when the rtDown code has changed. When a figure's code is changed from the viewer, hard-down only reruns that Python code block. We implemented hard-down as an extension to Python Markdown. Given an input Markdown source file, hard-down first passes all the context declarations. These are used to infer each symbol's scope, so that the prose annotations in the MathJax LaTeX output, the span tags around the symbol definitions in prose, and rtDown can all meet specifying the context. Then hard-down concatenates all rtDown code from the same context and compiles it into both executable code for the libraries and MathJax. Hard-down then searches for each symbol in the user's LaTeX derivations and applies the LaTeX command used by our MathJax extension, so that the derivation symbols can be queried uniformly. If the source contains the figure code, hard-down extension will extract them in the end. We added support for inline mathematical expressions by enclosing them in the $. We modified an bibliography extension to resemble the SIGGRAPH bibliography style. We also used the pandoc style YAML headers to specify metadata. The paper reading environment uses HTML for document reflow, SVG arrows for math augmentation, JSON output by the hard-down extension to visualize the symbol relationships and enhances the paper reading experience. We leverage MathJax extensions to store information for symbols and equations in the HTML tags generated by MathJax when displaying LaTeX math. This allowed us to access the symbols in a structured way from JavaScript, which implements the dynamic interactive aspects of our reading environment and styles the symbols using CSS. We converted a variety of SIGGRAPH papers and paper sections to hard-down. Our criteria for selecting papers was that they use linear algebra implementable by rtDown. The papers are from the past 5 years of SIGGRAPH and span geometry processing, image processing, visualization, simulation, and rendering. It includes 5 full papers and 9 papers for which we implemented single subsections. Out of the 14 papers we re-implemented, we only found code online for 7 of them. Among these, 4 are from the paper authors, and 3 are third-party implementations. Papers with an asterisk had implementations available. The rightmost column displays the total number of rtDown equation lines, and in parentheses, the number of rtDown blocks, and the number of inline rtDown formulas. We use the library generated by hard-down to replace functions in the original code for each of these 7 examples, and use input examples to verify that the results match. Each example in our evaluation includes hard-down source file, hard-down's generated paper reading environment, and hard-down's generated code library for C++, Python, and MATLAB. We also provide a link to the original paper for comparison and side-by-side screenshots. We conducted an expert study to understand how active researchers can make use of our hard-down and the executable code that it generates. We recruited 3 computer science PhD students. In our experiment, participants were given initial and follow-up questionnaires to understand their current practices and share their thoughts about hard-down. They spent a total of 24, 7, and 6 hours respectively, using Markdown over a period of 2 weeks. For the tasks in our expert study, the first expert wrote a function with conditionals to calculate the distance from hand to shape in 3D. The second expert solved an optimization problem for 3D snapping. The third expert wrote a tutorial for discrete elastic rods. This tutorial is now more readable due to math augmentations and can be used in addition to read, since it self-generates the code in any programming languages rtDown supports. At the conclusion of the study, we sent participants a follow-up questionnaire. 2 participants appreciated that writing in Markdown is similar to writing Markdown. 2 commented that writing math in rtDown is harder than with Markdown or LaTeX. 1 commented that the generated code compensates for the additional time spent writing the equations. All participants liked the dynamic reader features. 1 user said, Markdown is an excellent tool to share tutorials online. It highlights the vector dimension and variable meaning. Following all the vectors, matrices, and their dimensions is the hardest part of reproducing a paper. Most of the limitations they encountered were due to rtDown language limitations, such as limitations around the summation ranges. We fixed the cosmetic usability problems raised by the participants, like stale information being shown when an error occurs. We plan to address limitations in rtDown functionality. Since our goal is for Markdown to be adopted by researchers, user feedback will guide development efforts. We have demonstrated that Markdown is a useful, compatible document processor. One limitation of Markdown is that it does not consider pseudocode, iterative programming, or algorithmic steps described in prose. Algorithms are often needed to make formulas useful. Another limitation stems from the kinds of formulas that our extended version of rtDown can handle. In future, we also plan to support automatic or semi-automatic conversion from LaTeX to Markdown. Incorporating a proof checker could allow the verification of derivations, explore callbacks and delegates for expanding the abilities of the generated code, improve our reading environment to support active reading activities, such as annotating and comparing. In conclusion, Markdown is a low-overhead, ecologically compatible document processor. Markdown supports authors and improves replicability, readability, and experimentation. Participants in our expert study found uses for Markdown in their research practice. I'd like to thank anonymous reviewers for their suggestions, Seth Walker for helping design the reader environment, Zoya Balinsky for a discussion on related research projects, Zhecheng Wang, Xue Yu, and Jialin Huang for additional feedback. The research is supported by Canada Research Chairs Program, Sloan Foundation, and Adobe. Markdown can be used at all stages of research, from experimenting with the seed of an idea to writing the final paper. Thanks for listening. Please try our language. You are welcome to contact us in the future.